Yeah, good morning, everyone. Thank you for the introduction. Thank you for giving me the opportunity to present here today. It's a bit unfortunate for me to present after two experts of the field of ultrafast and antiferromagnetism. So our group is a group which background is basically on Spintronics. We have been interested in studying ferromagnets until now, and our lab is mostly equipped with different facilities that span a bandwidth from DC up to, let's say, maximum 50 gigahertz. However, recently we started to become very intrigued by the possibility of bringing Spintronics to faster time scales. And so I started to slowly approach the field of ultrafast, and I did that via a collaboration established with Nijmegen, with Alexei Kimel and Theo Rasing, where I spent a few months thanks to a Liverum International Network grant, which allowed me to learn a little bit about time-resolved terahertz spectroscopy. And then I went back to Cambridge, and I spent the past year building a time-resolved terahertz setup in Cambridge, which just very recently became operational. So the two works that I will present today are mostly from the time I spent in Nijmegen. So unless otherwise stated, all these measurements have been done in the group of Alexei Kimel. So what I wanted to cover today is something that has been interesting me from the Spintronics point of view, which is the possibility to extract spin information from an antiferromagnet or a zero magnetized element. And also the other question that intrigues me is, can we use this spin information to read out the antiferromagnetic state, and can we do this at picosecond timescales, so ultra-fast and electrically, so not optically. By electrically, I mean via the generation of picoseconds electrical currents. Now, there are several ways to approach this problem, and now my group is attempting to approach this problem from many different sides. But today, as I said, I will just mostly cover two experiments. The first experiment concerns the spin emission from a ferromagnetic alloy, even at the compensation point when this alloy has an overall zero magnetization. Now, the alloy of interest in this case is gadolinium iron cobalt. These kind of rare earth transition metal alloys are very important from the technological point of view. We can find the highest permanent magnets in this class of materials. And the reason is that when we combine rare earth with transition metals, both elements contribute to the overall characteristics of the material with positive contributions. Now, the origin of magnetism in transition metals and rare earth is very different. So while in transition metals, it originates from the itinerant 3D bands, in rare earth, magnetism originates from the partial filling, as we move along the period, of the very localized 4F bands. Now, when we combine several atoms of rare earth in a macroscopic sample, long-range magnetism is established via an exchange interaction mediated by the 5D bands. However, still the atomic properties, as far as magnetism is concerned, are retained. And this means unquenched orbital momentum. This means, therefore, high spin-orbit coupling, and this means, therefore, high magnetic anisotropy. Now, when gadolinium is then mixed in an alloy with iron, so it still contributes with a high magnetic anisotropy to the overall permalloy, but then still iron contributes to the alloy with a high TC, because determined by the strong exchange interaction between the iron atoms. On top of this, there is also an exchange interaction between the gadolinium and the iron atoms, mediated by the hybridization of the 3D and 5D orbitals. And this exchange interaction is negative, so there is the magnetization of the gadolinium atoms and the magnetization of the iron atoms are anti-aligned. But still, as I said, despite the fact that they are in an alloy, they retain very peculiar and characteristic properties due to the fact that magnetism has very different origins in these two materials. And we've seen yesterday in a nice introductory talk by Bert Koopmans that, for example, they have very different time responses to an optical excitations. But also the time dependence of the magnetization is different in the gadolinium and iron sublattices. And this results in a compensation temperature in which the two magnetizations are exactly equal and opposite, and therefore result in an overall magnetization, zero magnetization of the permalloy. Now, the material that we're interested in is a 20 nanometer thick gadolinium iron cobalt layer grown in contact with a 2 nanometers platinum layer on a silicon nitride buffer layer, and everything is again capped to avoid oxidation. Now, there is a strong uniaxial anisotropy with an easy axis in the out-of-plane direction. So this means that if no magnetic field is applied, the magnetic moments will align in the out-of-plane direction. Now, the experiment that we did was to basically investigate in the picosecond range the spin emission from such an alloy by using terahertz time domain terahertz spectroscopy. Now, we've seen yesterday, also in the introductory talk by Bert, that when we excite a ferromagnetic metal with an optical pulse, a bunch of different things happen, among which the magnetization is quenched. But among these things, there is also the establishment of a superdiffusive spin current, which we can collect by using a heavy element, and translate this spin current into an electrical pulse, which then results in an electric dipole emission in the terahertz range, which we can detect by electro-optic sampling. The same is true, we expect this to be true in our ferromagnetic alloy, which in general, as a function of temperature, is in a non-compensating status. So we have a net magnetization. So we expect it to behave as a normal ferromagnet. And therefore, we expect that when this alloy is excited by a femtosecond optical pulse, in our case in the 800 nanometers wavelength range, we expect a terahertz to be emitted directly proportional to the emitted spin currents. Now, because this terahertz is generated by the inverse spinel effect, it is directly proportional to the in-plane component of the spin polarization that reaches the sample. So in order to guarantee an in-plane component, what we must do is to apply an external field in order to rotate the magnetic moments away from the out-of-plane easy axis in the plane. So during our experiment, we will have an in-plane magnetic field. Now, these are the results. So the first thing that we notice is that we see a terahertz emission. So we probably see spin emission from our ferromagnetic alloy. What we see is that if we invert the sign of the external magnetic field, we also see that the emitted terahertz flips signs. And also we see a flip in the emitted terahertz sign if we flip the direction of the sample with respect to the optical excitation. Now, both of these observations are in agreement with the symmetry of the inverse spinel effect. In the first case, by flip here, I have to say we are at room temperature, so we are away from the compensation point, so we have a net magnetization. If we flip the direction of the magnetic field, the net magnetization flips as well, and we therefore expect opposite spin polarization of the current injected into the platinum. In this case here, when we flip the direction of the sample, we expect that the direction of the spin current flips, and again, since the inverse spinel effect voltage is given by the cross product of sigma of the spin polarization by its direction, then we again expect a change in sign. So both of these observations are in agreement with the inverse spinel effect, and they seem to indicate to us that the terahertz that we measure is consistent with a spin pumping experiment from the permalloy induced by the optical pulse. Now, this is probably the most important result of this experiment, where I show the amplitude of the emitted terahertz as a function of magnetic field, and at two different temperatures, one below the compensation point. The compensation temperature is about 240 Kelvin. So the blue line corresponds to a temperature below the compensation point, and the green line corresponds to a temperature above the compensation point. So if we fix the magnetic field in one direction, for example, if you consider 1 Tesla here, so we're basically pinning the net magnetization along the direction of the field, we see that by crossing the compensation point, the sign of our emitted terahertz flips. So this immediately suggests that the emitted terahertz signal that we measure is not correlated to the net magnetization, as we would expect for a ferromagnet, but it is instead correlated to the magnetization of one of the two sublattices. iron or gadolinium. What we have indeed is that below the compensation temperature, the magnetization of gadolinium is the predominant one. So the magnetization of gadolinium will be the one aligned with the net magnetization pinned to the external magnetic field. Above the compensation point, the iron magnetization is the dominant one, which will be then the one aligned with the net magnetization pinned in the direction of the field. So now the reasonable assumption that we can make is that indeed the emitted spin currents are mostly coming from the iron sublattice. And it is reasonable to assume that because we know that magnetism in gadolinium and iron has very different origins, and it is much more energetically favorable to promote spins, to promote carriers from the itinerant 3D bands than by promoting them from the much more localized and energy-buried 4F bands in the gadolinium. So what we have is that when we excite this permalloy by an optical pulse, the two magnetic species respond differently and contribute differently to this super diffusive spin currents. So the bottom line here is that then, even at the compensation point, when the overall magnetization of the permalloy is 0, we would still expect a spin emission from the permalloy because the magnetization of the single sublattices of the iron is non-zero. So we would have a zero magnetization spin emitter. If we do the experiment, however, by varying the temperature and starting to approach from below, in this case, the compensation temperature, what we see is a reduction in the sign of the emitted terahertz. But this doesn't have to do anything with the fact that we have less spin current emitted, but rather with the fact that as we approach the compensation point and the magnetization goes to 0, obviously the Zeeman interactions are reduced and the moment starts to align again in the out-of-plane easy axis direction. And this means that we no longer have an in-plane components of the emitted spin currents that we need in order to generate an electrical pulse via the inverse spinol effect. This data is very well reproduced by adopting a very simple macrospin model in which we simply include the Zeeman interaction of the two magnetic species, gadolinium and iron, the mutual exchange interaction, and magnetic anisotropy for each one of them. This graph here represents the theory model, which we simply wrote on Mathematica, and which shows the in-plane projection of the iron magnetization as a function of magnetic field. As you can see, it reproduces very well our terahertz signal, which is again another confirmation of the fact that our terahertz amplitude is basically connected not to the net magnetization, but only to the magnetization of the iron sublattice. Now, this brings me to the second experiment that I would like to tell you about. It still concerns the spin emission from a zero magnetization, magnetic material if you want, but from an antiferromagnet. This is something that really is interesting us a lot. And there are several ways, as I said, in which we can approach this. One way that has been explored by several groups recently is the spin-Seebeck effect. So what people have been doing is measuring the spin-Seebeck effect, longitudinal spin-Seebeck effect, in heterostructures made by an antiferromagnetic dielectric grown in contact with a heavy metal, and under the presence of an out-of-plane temperature gradient generated by some heaters. Now, what all of these measurements, which were carried in the DC limit, suggest is that a net spin emission can be achieved from the antiferromagnet only if the antiferromagnet has a non-zero magnetic component. So this is clearly seen here, where you see that the longitudinal inverse spinol voltage perfectly overlaps to the magnetic field dependence of the longitudinal voltage, inverse spinol voltage, which is directly proportional to the amount of spin current emitted into the platinum. So what we have is that if we apply magnetic field along the easy direction, in chromium oxide in this case, before the spin flop field, where the moments are aligned along the field and no net magnetization is established, we also see zero longitudinal voltage. However, just above the spin flop field, the magnetic moments of the antiferromagnet turn perpendicularly to the field and then start to count towards the field, developing a net magnetic moment. And we consistently see an increase in the longitudinal DC voltage. Now, when we talk about antiferromagnets, obviously the intriguing aspect is also the much faster dynamics. So what we were interested in doing is then now to translate these studies of the spin emission induced by a temperature gradient, if you want as well, to the picosecond time scales. So obviously this requires different techniques from those that have been used in the DC limit, and obviously this requires time domain terahertz spectroscopy. So we wondered what would happen, for example, if a sample made by the electric antiferromagnet grown in contact with a heavy metal, in this case platinum, was excited by an optical pulse. Now, this optical pulse would be partially absorbed by the antiferromagnetic electric, but would be mostly also deposited on the heavy metal, exciting, increasing the temperature of the electrons, so effectively establishing a temperature gradient. And we were wondering if this would then result in a spin emission from the dielectric, which would have then resulted into a terahertz emission. Now, the dielectric in this case belongs to the 3-fluoride family, it's potassium nickel fluoride. It has a cubic perovskite structure where the magnetic moments which reside on the nickel atoms can align along one of the 3 cubic directions. Now, these are, I already apologize, these are very preliminary results which were made probably in 2 days of measurements, but I still want to present them today, although we will continue measuring in this direction because they present some interesting notes and maybe some interesting opportunities for these discussions. So the first thing that we notice is that we see terahertz emission. So there is something that results in a terahertz emission. We also see that, again, if we flip the direction of the sample with respect to the pump excitation, the sign of the emitted terahertz flips. And this, again, as I said before, is in agreement with an inverse pinhole effect symmetry. On top of this, we also see that when we pump the sample from the platinum side and we read out the terahertz emission through after it has crossed or through the antiferromagnet, we see that on top of the main terahertz emission, there is also some coherent oscillations that are observed and which are not observed in the first case. So these correspond to an absorption peak at about 1.5 terahertz. And further confirm the fact that the platinum is the source of the terahertz. And being the source of terahertz, then when the emitted terahertz crosses the antiferromagnet, we only see this absorption of 1.5 terahertz, which we don't observe, on the other hand, in this case, where we directly measure the terahertz after the platinum without going through the antiferromagnet. So these two observations seem to coherently tell us that the terahertz is indeed generated by the inverse pinhole effect. In this graph here, we show how the amplitude of the emitted terahertz scales with magnetic field. We have only measured at high magnetic fields in this case, where we see a linear dependence with the magnetic field, which is consistent with the DC measurements of the fact that the emitted spin currents are proportional to the net magnetic moment established after the spin flop, which in this case is at about 0.5 Tesla. So after which the magnetization of the material linearly increases, and in agreement we see a linear increase of the emitted terahertz. Now, however, the question that we were originally interested in is understanding whether any magnetic excitation within the antiferromagnet would also lead to the emission of a spin current. So we need to understand really what the origin of this spin current is. And this material, potassium nickel fluoride, is particularly intriguing in this respect because we can very easily decide whether to excite a non-coherent or a coherent magnetic population. Now, this work, really nice work was from Davide Bossini on the same material. Basically, what he did was a pump probe experiment in which he was pumping the sample at different wavelengths and monitoring the change in ellipticity of a probe pulse induced by magnetic linear birefringence. So basically, this was directly correlated, was giving answers on the magnetic excitations that were optically induced in the sample. Now, the reason why this material is interesting is because its absorption characteristics as a function of the wavelength are very different. So we see a series of absorption peaks at some wavelengths alternating to transparency windows. Now, what Davide observed was that if the sample is pumped at a wavelength in correspondence of the transparency window, then coherent magnets can be excited. Whereas if we pump the sample in correspondence of an absorption window, these coherent oscillations are superimposed to a much larger background, which is associated to the excitation of non-coherent magnets. Now, the power of this technique is in the fact that by his probing method is susceptible, is sensitive both to transverse and longitudinal modifications of the Snell vector. So what he associated was that these oscillations here could be associated to transverse oscillations of the Snell vector induced by a coherent mode, whereas this background here was associated instead to a reduction or expansion of the length of the Snell vector, which is instead associated to the excitation of a non-coherent magnetic population. Now, the reason why this is only observed when we pump in correspondence of the absorption peak is because, in this case, localized electronic excitations are also induced, which then relax in a photon bath, and which then starts to exchange energy with a time scale of about 100 picoseconds with the magnetic population, effectively increasing its temperature. Whereas in the other case, when we pump in a transparency window, these electronic transitions are no longer induced, and a coherent excitation is simply induced by impulsive stimulated Raman scattering process. Now, so in our case, as you can see here, the time scale to establish a magnetic population here, a non-coherent magnetic population, are in the range of 100 picoseconds. So the way by which we detect, so our measurement technique spans a bandwidth between about 200 gigahertz up to, let's say, 5 terahertz. So we're not able to resolve this slow dynamics. So our terahertz is not correlated to the excitation of a non-coherent magnetic population, as instead was inferred in the DC measurements. And we also don't see any signature from this coherent mode. Our results seem to be much more reminiscent of another work in collaboration with Tobias Kampfert in Berlin, in which the ultrafast spin-Seebeck effect was measured in a YIG platinum layer. So in this case, instead of having an antiferromagnetic dielectric, we have a ferromagnetic dielectric. But the experimental layout is exactly the same. So the sample was pumped by a femtosecond pulse, and the terahertz emission was measured. Again, by measuring in different directions of the magnetic field, the emitted terahertz was consistent with the symmetry of the inverse spinel effect. So the emitted terahertz flipped sign. And actually, the amplitude was directly seen to be correlated with the net magnetization of the YIG. And on top of this, it was observed that the emitted terahertz would flip sign if platinum was substituted with tungsten. So again, in agreement with the inverse spinel effect symmetry. The other element that really seemed to point towards the inverse spinel effect was the fact that the magnetization as a function of temperature and the emitted terahertz as a function of temperature were following two different power laws with respect to temperature. And this was also observed in the DC limit. So now the question is that was explored in this work. So what's the origin of this ultra-fast spin emission from the ferromagnet? And this was resolved by looking at the time dependence of the generated spin current that then gives rise to the terahertz emission, which was obtained by doing a complex deconvolution of the measured terahertz by the response function of the detector and the transverse function. But what they observed is that the time scale in which this spin current is generated are in the order of 100 femtoseconds and seem to correlate very well with the electronic temperature, which was instead measured by doing a reflectance experiment. So the reflectance of platinum in this case is directly proportional to the electronic temperature. So the conclusion of this paper was that the electronic temperature in the platinum excited by the optical pulse plays a crucial role in inducing spin transfer from the ferromagnet. Now, with this, I think it's time to conclude. I would like to acknowledge basically many people from Nijmegen, and of course Davide, who became my mentor in magneto-optics, and Tobias in Berlin, and of course the funding body. Thank you.